All right, so let's say you have a ball and you drop it from rest. Okay, let's see what we can determine from that. Well, first thing you would want to do is draw a motion map. Looks something like this, right? And if it's from rest, I'm going to put an extra dot up there to show that it wasn't moving at the time it was dropped from rest. Okay? And these arrows are getting larger. Those are my velocities. Now my acceleration arrows should all be identical while I'm modeling the object that's in the air, right? So there it is. There are my accelerations. I've tried to just draw arrows that didn't change length. Okay? And I should put maybe an axis, coordinate axis on here. Now, since we're going to be dealing with two-dimensional motion, I'll call this y. And I'll have my object start from 0 position, just to make that simple. Now let's do a stack of graphs. This would be position, velocity, acceleration, sum of the forces. Okay, acceleration, velocity, position. Okay, so when I draw the stack of graphs, I'm going to start with the easiest, and I made down positive, so I'm going to make my acceleration positive, and that means my net force graph looks the same. Okay, and my velocity graph should look like this, and my position graph should look like that, right? And then if I take this area here, I'm gonna get my change in velocity, and that should be equal to AT. What I find interesting, the graphs only really show magnitudes of our vectors, but once we go into the fundamental relationships, acceleration and change in velocity are vectors, so I can argue that acceleration is down, therefore my AT vector is down because time doesn't affect the direction of that vector. And this vector is exactly identical to my change in velocity vector. And that vector, since my initial velocity is 0, is identical to my final velocity vector. I think that's kind of nice. So all those vectors are actually identical. And if I had any of those variables, any of them, I could find the rest, right? If I had A and T, or if I had delta V, or if I had V final, I could find time, for example, if I knew how fast the object was going at the bottom. Knowing that these three vectors have the same exact lengths is actually quite useful. Now I can highlight this area and realize hopefully that that's my displacement in the y direction. And displacement, as you know, is a vector, right? And that's got to be equal to, the height of that triangle has to be AT. So what I'm talking about is AT squared over 2, right? Now, A again is a vector down, and T squared doesn't change the direction of that vector. So my displacement, you already knew this, but it has to be down, right? And my 1/2 AT squared vector, in other words, my 10t squared vector, no, sorry, 5t squared vector, because A is about 10 meters per second squared. So I'll just leave this as 1/2 AT squared vector. And it's also kind of interesting, if I start from rest, my final position vector, because delta y is equal to final position minus initial position. So this tells me also where I'm at relative to 0 position. Sorry, not x at 0. That's my final position. So these are all the things we know from just an object being dropped from rest. And key part of this class is going to be understanding these vector relationships. I think this is going to help you a lot with really doing the harder problems. Even though this is a simple one, you'll see that these vector relationships get more complicated, but they're just adding or subtracting vectors. Anyway, hope that helps. That was a ball drop from rest, and have a good day.